Let's define over and undershooting. The overshoot is how far past the target point the robot tends to go as it is responding to an error. Let's look at the graph. We have a set point where the robot needs to be. And the robot starts moving. The motors of the joint begin to turn. So the robot makes the turn. It goes to that particular position. But because of it's a mechanical device that is on its own inertia, on torque, that if we don't design the path, the transformation between point A to point B in space, sometimes we go over the points that we want to go. That over is the overshoot. And when we go over it, we need to come back to the position because we went beyond it, we need to come back. And when we come back, we go over, but from a different direction, the opposite direction, so we will go to undershoot. So overshoot, undershoot, overshoot, undershoot. At the end, we will get to the set point that we need to be. But that creates a problem. Because this overshoot and undershoot, meaning that the motors of all the joints working in different directions in a very short amount of time. So from electricity point of view, it is a problem. It takes time for a voltage to stabilize. From a mechanical point of view, it creates a problem because that mechanical structure is being stressed. Especially, and we're talking about a period of time of less than a second. This overshoot, undershoot, overshoot, undershoot can kill, can break the mechanics of the robot. Let's learn how to overcome and minimize, at least, this aspect of over-undershooting. And to understand a little bit deeper the overshoot, undershoot aspect, we have to understand the settling time. And here in this particular graph, the settling time is presented very, very, very clearly. It is in the bottom. And it's the first time that the robot came back within the error band. That band on the top, being marked on the error band on the top right, is the error band that at the end, eventually, that set point position will be. We want to be exactly on the position that we plan, but we allow some kind of a threshold, a top threshold and a bottom threshold, some range, a band, we call it an error band. So the very first time after we had the overshoot that we came back to the error band, this is what we call a settling time. And the rise time, and this is specifically why we marked it in red, is the amount of time that the robot, it took the robot to reach that set point position. Finally. And we understand the overshoot, and in this particular graph, there is no undershoot. There's no undershoot because the graph or the robot did not cross the lower threshold of the error band. So there's an overshoot and it's getting stabilized within the error band. There's not undershoot. And this is a simulated test of overshooting and undershooting. And we will see the difficulties, how to actually deal with it. And we just took kind of a humanized hand in order to simulate a test. And let's say that this hand has basically two tasks. The handle is fixed at the start and subject either squeeze the handle, which is task A, or generate an isometric exterior torque, task B. Altogether, the angle should be 60 degrees. And it's divided to 15 and 45. The timeline on the bottom is basically the test itself. We have 5 to 10 seconds of what you call waiting time, waiting for this command to take place. Once a go signal take place, then within 800 milliseconds, 0.8 of a second, we need to actually cross these 60 degrees. And then we have to hold it at the end when we get to the point B. We have to hold it between 1 to 10 seconds, and then we have to, when we hear a beep, we have to rest it and go back to the original place within 6 seconds. This is the simulator test, and let's see the effect of it. It's kind of a repetition to the previous one, but just to say that there are two sections. And the timeline is a very critical timeline. 800 milliseconds, we should not pass that. And the beep, meaning that whenever there is a command, that particular robot needs to make a decision, a quick decision to go back. And there is a turnaround time between the beep generation and the movement generation. Because it's an electrical and mechanical system, the robot, and because there is a computer, external computer, control it and command it, there is what you call propagation delay time. And if we still limit ourselves to 800 seconds and a beep generation, meaning a command generation, that means that just before the finish of the 800 milliseconds, just prior to get to the 800, we still have to make some decisions in order to assure soft landing. And within that simulated test, we see the movement torque profile A, and then the mean torque profile B, and the two different tasks that we're talking about. The upper graph is a 60 degrees range that we need to make the object moves with our hands. And that 60 degrees is basically not longer than 800 milliseconds. And as we can see from a torque point of view, that once we have a start, after waiting for about 10 seconds, we get a start command, the torque goes a little bit high. The torque becomes very negative, below zero, and then when we get to about 50 degrees, we slow down the process, we decrease the torque, and we get to the 60th degree exactly after 800 milliseconds without overshooting. That's because 10 degrees before the end, we change the speed of the path, we change the position of the gripper in order to reduce the torque, and that particular part between the degree number 50 and the degree number 60 is what we call the soft landing. You have to keep in mind, for every movement of the robot, there should be a graph like that in order to assure a soft landing. That particular part, last part between 50 and 60 degrees, is a programmed and planned soft landing characteristics of the path. Because we want 0 degrees torque when we get there, meaning no under and overshooting. And the graph on the bottom is basically several times that we do this test. We actually repeat this test tens of times in order to test the repeatability and the uniformity of the robot. And after these so many tests that we do, going back and forth and back and forth and back and forth within 800 milliseconds, look at the graph. There is the behavior of this mechanical and electronic system, the robot. There is a bunch of curves, but we actually look at the mean curve of the graph. And there is a threshold. There is an arrow band. We have to stay within the arrow band. So we do this 40 times, 50 times, 60 times in the test to see how uniform the robot is and to see if we really designed the soft landing part of the path properly. I would just like to add one point. we see here several graphs, several paths, several type of behaviors of soft landing and advance from point A to point B, which actually add up to a mean. But in this particular seminar, we don't get into the mathematical expressions, mathematical formulas of describing each graph and each path. It's just the combination of them giving us the mean one of all. Now this slide, in terms of the overshoot and undershoot, it has what we call ringing. We present something that's called ringing effect. And what is ringing effect? We have a position 1 and position 2 and go back to position 1 for the robot. So your robot actually goes from point A to point B and come back to from point B to point A. And we can see it. In this particular example, point A and point B are 2 points vertically have different y's. The point, the first position is on the top. The second one, the central part of the graph, is something on the bottom, and then the robot goes up again. So the robot goes from top to bottom and comes back up. So we have falling undershoot and falling overshoot. This is when we fall. And the reason that we have this ringing effect is because we have the gravity being added to the total weight of the robot, as opposed to the other point, when we go up, the gravity actually is being subtracted. The gravity effect is being subtracted. Because we have 2 sets of movements. One is with the direction of the gravity, and one is the reverse direction of the gravity. We have different ringing effect. And we can see the overshoot and undershoot in each part. When we go up and the gravity is subtracted from a set of weights, obviously we need to have some set of calculations to take into account when it comes to soft landing and torque. But when we go down, the soft landing should be much more significant, because it's the same direction as the gravity itself. And the ringing effect is that overshoot, undershoot along the line to such a degree that there's almost no resting time. We can see that the ringing, is for the entire length of when we are there in the position, no matter if the position on the top or position on the bottom. That ringing effect is all that time. So the robot basically is not stable at no time. It goes up, has overshoot and undershoot there, and when the time comes to go down, even if we have overshooting and undershooting there, we actually taking it down, and this is being accumulated. And we actually can see that when we go down, the amplitude of the overshoot is bigger than the amplitude of the overshoot when we go up. Very, very easily we see that the overshoot, undershoot, the ringing effect takes the entire resting time. That means this process is never stable. Very bad in terms of accuracy, life cycle cost of the robot, etc., etc. Remember, ringing effect is where the overshoot, undershoot takes the entire time of the place position or the peak position. And when it comes to overshoot and undershoot, there's something that's called quality coefficient, Q. Let's look at the graph. Q equals 0.1, meaning we have a slow, gradual process of movements from point A to point B. This is the red graph. No overshooting, no undershooting, a very smooth one. When Q is equal to 5, and this is the green graph, is when we have the maximum overshoot and the maximum undershoot. It will stable and we will get to it, but far after we go to 25 microseconds in this particular graph. So if you really, really want to assure that it will take 25 microseconds for the robot to be stable, we work with lower Q, quality coefficient. The lower the Q, the more stable the system is. It will take somewhat longer, but it will be stable. So the process of movement from point A to point B will be more reliable in terms of the life of the robot and in terms of the accuracy, the precision of arriving at the place and peak position. I want to pay your attention to what you called path time in terms of overshoot and undershoot. If we need to move to turn a robot from 36 degrees to 76 degrees, a 40 degrees range, and we want it to, we limit ourselves to 1.4 milliseconds for that particular movement. We have to divide this 1.4 milliseconds into segments in order to assure that we will be stable, no overshooting, no undershooting at the next position. For this we need a Q, quality coefficient. That particular Q is being given to me by a set of tables because of the following things. Number one, there are technical specifications of the robot. We know the robot that we're working in. Technical specification of the object that we want to be, the object that we want to pick or place. That means we can calculate the torque, we can calculate the acceleration and deceleration. These are physical and physics aspects. Nothing to do with programming. First of all, we know the physical parameters and aspects of the task that we need to do. Once we know our robot and its technical specification, once we know the starting point and the ending point, and the time that allows to us to go from A to B, we physically can calculate torque. And once we have the torque and the mechanical aspects of the robot, we can go fetch the Q value from tables. That Q value from tables, we apply it into the program, into the robot program, which we program offline in a computer. So that particular Q determine what kind of overshoot, undershoot characteristics we'll have. And it's basically a generation of the calculated torque and the calculated mechanics that we have for that particular task. So it's not very, very difficult to design a path with a known amount of over and undershooting. Just to repeat that and to summarize that. We know the path, we know the allocated time to do the path, we know the robot, we can calculate the torque and all the mechanics and physics aspects of it, acceleration, deceleration. From all these, we get the Q, we plug the Q into the program. That's how we can control the path. And in this particular graph, this is how can we control what will be the degree any time within that range. So from 0 to 1.4, we can be in 1.15, we can be at 45 degrees, and 1.2 milliseconds later, we can be at different degrees and get to the target. Using Q that was given to me by tables when I plugged in the torques, acceleration, deceleration, physical parameters.